Hello, I'm Tobi Vaudrey, presenting this video on robust scene flow using stereo sequences in near real time. Generating three-dimensional velocity from a moving platform is a difficult task. Not only is the background moving, but also objects in the scene. We achieve this using nothing but binocular stereo sequences, and managed to obtain running times of 10 Hz. Here is a typical driving scene. Notice how the background moves differently compared to the moving participants. The 3D vector reconstruction shows moving points as red and stationary as green. You can notice that the objects have their vectors bundled together and that the car and background are stationary and the pedestrian is moving. You can also see that we are not constrained by the original camera view in this 3D view. I will now outline how our algorithm works. From the diagram shown, you can see that we only use two sequential stereo pairs and the disparity image from the first pair. Stereo disparity can be calculated using an FPGA or other such hardware. This requires no additional computational cost. Using this information alone, we can efficiently compute scene flow. This yields two outputs, disparity change and optical flow between frames. The main contribution of our approach is the decoupling of motion and distance estimation. The bottom pair here is the first pair and the position is set via stereo. We handle occlusions and missing stereo data efficiently in our motion estimation scheme. For the left pair, we use the typical intensity consistency assumption employed in most optical flow approaches. However, for the right pair, we use disparity and disparity change to help drive the equation. To ensure that we have consistency in the second pair, we employ a soft disparity constraint at this time. The two bottom equations that use disparity are only taken into consideration if stereo information is available. This is shown by the C function. We form an energy minimization equation using these constraints. We further employ a smoothness constraint and use a robust approximation of the absolute function for all minimizations. This system of equations is solved using successive over-relaxation. We now show the results over the entire sequence. Again, red is moving and green is stationary. Notice how the vectors for the van are closely bundled together and all depict approximately the same magnitude and direction. Vectors in the background and on the road are mostly shown in green, showing that we do obtain accurate stationary values. There are some minor errors in the background and on the road, and also when there are large camera movements, but generally the motion is well predicted and similar motion vectors are clustered together accurately. From this information you can now tell where an object will be moving to in the next few seconds. The running pedestrian can be clearly distinguished from the parked car. This is very important for driver assistance decision making. If we focus on the pedestrian and reduce this color scheme to a narrower band, we can now see precise movement of the pedestrian. The leg on the ground is shown in green and the other leg is shown moving rapidly in red. Also, the arm is moving faster than the body. This is the movement you should expect from a running person. Here is our final video showing a typical scene where we are following another vehicle. A speed of 0 is shown as green and a speed of 36 km an hour is shown as red. The original video can be seen in the top left corner. The lead vehicle has vectors clustered together and depicting the same magnitude and direction. Furthermore, all parked vehicles are shown as stationary as they should be. If we zoom in on the car from above, the vectors can be seen shown similar magnitude and direction. No post-processing has yet been conducted on these results. Our scene flow algorithm employs a GPU implementation and uses an FPGA to provide stereo correspondences. This yields running times of 10 frames per second. For more information, refer to the reference or contact the author shown.